Okay, let's continue. So now we're gonna move on to the next topic, which is asymptotic normality of the maximum likelihood estimator. So, uh, theta hat n is the MLE of theta true parameter. So that is solution, right? Sn is now defined this way. So theta hat n is the solution to Sn theta equal to 0. So that is called the score equation, right? So rigorous theory is quite involved. So I will just sketch the idea for the proof. The idea is to make life easy, we'll just consider scalar theta, but extension is similar. So for the starting point is to use the fact that the MLE converges in priority to theta null, right? And then because this is true, right? Because this is true, the equation is true by the definition of the MLE. So we can apply Taylor expansion around theta null, right? So we just take the second order Taylor expansion of this guy, of Sn theta hat. So this is the function. So you view it the function of theta hat n, and then expand it around the theta null. So this is the first constant part and first linear part and quadratic part, and then first order partial derivative is second order partial derivative, and then the value is the sum here point between the 2 points, right? Now, using this, you can basically use algebra to obtain equation 1. So this is exact equality. And now we're going to look at one by one. So the numerator part, you can notice that this Sn theta null, right? Sn theta null is just a linear function. I mean the summation, the sample mean of theta null. So S theta null. So it's a sample mean of a random variable S evaluated theta null. So then the expectation of S theta null at theta null, because the assumption is what? Assumption is x1 to xn from density theta null, right? So that is the assumption. So then the expectation is as theta null. So this is 0. So mean 0, and variance is theta null. Okay. Theta null. So then because it's a sample mean, so we can just apply the central limit theorem to obtain the asymptotic normality of the numerator part. Now to check the denominator, you can see that okay, so we have a 3 component. One is denominator, first term, second term, third term. So we'll just show that this first term will converge to minus information matrix. Second term will converge to 0. Third term is bounded in probability. So that's what. So denominator. Since this is just another sample mean of S dot, right? So then a sample mean converges in probability to the expectation, the population expectation, and the definition of this population the expectation is minus information matrix, and then second term it converges to 0, right, by the consistency of the MLE. Third term we can establish. So the last term, the third term, we want to show that this one is bounded in probability. And to show the bounded in probability, we require some assumption. So we'll do it later. So we'll just for now we'll just accept this equation 2. So then once you do that, then the denominator of 1 simply converges improperly to minus zeta null, right? Minus I zeta null. And then so this one converges to normal, right? And the denominator converges to a certain constant, converges improbability to constant. So then we can apply Slutsky theorem to obtain this result, right? So the numerator, so this is a numerator variance, and the denominator goes to constant, and then we square it. But since we have this lemma 1, right? The previous lemma here. So this lemma basically says that variance is cancelled with information. So then this is the result. And then for this is for scalar, but for vector case, it's just the inverse of the information matrix. So that is the result. So now what we need to show is to establish second equality. The second equality is to show the second one. This one we need additional assumption. So the additional assumption is 3 times differentiable as a function of zeta, and then this is bounded. So third order of partial derivative is bounded by an integrable function, and for at least in the neighborhood. So this is ball. So in the C neighborhood. Okay. So first there exists some C, and so this is zeta minus C, right? Zeta plus C, or zeta, something like that. So to prove that, first, so what we want to prove is that S dot n zeta tilde, right? So we want to show that this guy is bounded in probability. Wish to show. Okay. So by the way, what is this? This one is this is. So let's write it more clearly. I'm sorry. Is the definition of this one is zeta 3 f log f xi zeta evaluated at zeta, right? So this is the definition. So if you look at this, tilde n, and then first we first okay, let's do this first. So first we want to show check that this one converges to this one, right? And also tilde n is okay. So we'll first need to check. That's not difficult. So because zeta null and zeta hat converges to zeta null, right? But zeta tilde is always within these two. So if zeta hat converges to zeta null, then zeta tilde will converge to zeta null, right? And so then that means we can always, so given the C, this C, so we can actually C will be always 1 minus epsilon for all, right? Something like that. So we can always make this happen. So that means we can make it bounded by, because this property holds for all zeta within this ball, right? So that means because zeta hat tilde n belongs to the bill, belongs to zeta null and C, right? So we can make it so this one, and this guy converges to expectation, converges in priority. So that means which means that is less bounded by for sufficiently large and 2. I mean, okay, to be rigorous, we can, right? This probability, okay, this probability will be always less greater than 1 minus another epsilon. So if you choose and maximum n1 and n2, then basically this guy, right? So what we want to show, this guy will be this guy will be bounded by, so for all n. So that is